This is EE698I, Mixed Signal IC Design, and this is lecture number 15. In the last capacitor amplifier, and we came up with the circuit when we tried to transfer the charge stored in our sampling network completely to another capacitor. So this was our sampling network. This switch is clocked at 5.1, and this is clocked by an early version to prevent signal dependent charge injection. And we wanted to transfer the charge stored at this node completely to another capacitor. And we do that by connecting it to an infinite capacitor, which is emulated using an OpAmp negative feedback. And these two plates of this capacitor CS will also be reset during the phase 5.1. Right? And of course, we transfer this charge during a phase 5.2, and both 5.1 and 5.2 are non-overlapping clock phases. So if I say this is the clock, and let us say when the clock is high, we have 5.1 active, and this is the phase when which 5.2 is active. So what will happen during the phase 5.1? The capacitor here samples the input voltage while this capacitor is reset, right? So if I call this time instant as NTS, the voltage sampled across the capacitor is Vin of NTS, right? So this is the sampling instant. Okay. So this time instant will be what? This will be NTS plus TS by 2, because this is TS by 2 long, right? So during this time period, when 5.2 is active, what will happen to the output? Well, the output will start from 0 and will slowly rise exponentially and reach the final value, which is C by CF times Vin of NTS, right? And what is the time constant? Time constant is R on times C, where R on denotes the on resistance of the switches that are active during the 5.2 phase. So it's essentially the on resistance of these switches, right? So this output is ready at this time instant, that is at NTS plus TS by 2, right? So the output voltage V0 at N plus half into TS is simply C by CF times Vin of NTS. Okay, so the input that is sampled at NTS is available after a delay of TS by 2 and is amplified by a factor of C by CF. And here we saw that the time constant is R on time C. And why does this make sense? Well, please note here that if R on is not there, what will happen? The output voltage will instantly jump to this final value, right? Because the capacitor would have instantaneously transferred its charge to this capacitor CF, right? But now with finite R on, the rate at which the output voltage increases depends on the current that is flowing through the capacitor CF, and this current will in turn depend on the rate at which this capacitor C discharges, right? And this rate is determined by the total on resistance times this capacitance. Okay. So in this, we know how to implement each of these switches. So let's now see what to do about the OpAmp here. And please notice that the OpAmp, as we have shown here, or as we have considered here, is an ideal voltage controlled voltage source. That is, it has an infinite input impedance and a zero output impedance, right? So let's see what are the possible candidates for this OpAmp. The simplest architecture the OpAmp can take is a differential pair with a tail current source and with a PMOS current mirror load. Right? This you would have seen in your microelectronics or analog circuits course. And the output is given to a source follower like this. This is the current source transistor, right? And this source follower acts as a buffer and provides a low output impedance. So this is the positive terminal of the OpAmp. This is the negative terminal, and this is the output voltage. So what is the output impedance here? Our out is roughly 1 over GM of this transistor, right? And when GM is large, this output impedance is very small, and that's what we want. Okay, so in this circuit, let us see what is the minimum and maximum voltage the output voltage V0 can take, while all the transistors remain in saturation region. Right? And for this first, let us ignore that we have this buffer, okay, and say this is our output voltage V01. So we'll see what is the minimum and maximum voltage V01 can take. So for V01, what is the maximum voltage? Well, maximum voltage is VDD minus the minimum of this source to drain voltage. Right? And what is this source to drain minimum voltage? That is simply source to gate minus the threshold voltage. Okay, and this we'll call as the overdrive voltage or simply V overdrive. Okay, so the maximum voltage V01 can take is VDD minus 1 overdrive voltage. Similarly, what is the minimum voltage it can take? Well, when V01 reduces, the NMOS transistor might go out of saturation. So the minimum it can take is 1 minimum VDS and 2 minimum VDS. So this is simply 2 overdrive voltage. Okay. So now we'll do the same thing for this output V0, which is the buffer output. Right. So let me just push it up slightly. Right. So this is my VDD. So for V0, what do we have? What is the maximum voltage V0 can take? Well, notice that the drain of this transistor is at VDD. So the gate at max can go to a maximum of VDD minus the threshold voltage, right? So which means the output V0 will be this VDD minus VTHN minus 1 gate to source voltage, right? And this we can simply rewrite it as VDD minus VGS minus VTHN plus VTHN minus VTHN, right? So this is simply VDD minus V overdrive minus 2 VTHN. And similarly, what is the minimum voltage it can take? It is the minimum of this VDS, which is again 1 overdrive voltage, right? From this, we can clearly see that the maximum voltage here is reduced by 2 threshold voltages compared to this guy, right? And the minimum side, this seems to take 2 overdrive. But again, this is not a great loss because overdrive voltage will be very small compared to the threshold voltage here, right? And also, if we use a 2-stage OpAmp, what we'll do is we'll, instead of taking this as the output, we'll give it to one more stage. Say something like this. This will be some bias voltage, and this will be the output, right? And in this case, the minimum voltage can be 1 overdrive voltage, right? So to get some better feeling, let's take some values and see what these values turn out to be. So let's say VDD is 1.2 volt, and I choose all the overdrive voltage to be around 100 millivolt, and threshold voltage is say around 0.4 volt. So what is the maximum output voltage range? That is VDD minus 3 times overdrive voltage. So that's going to be 1.2 minus 0.3, that is simply 0.9 volt, right? For V naught, this guy. So what is this? This is 1.2 minus 0.1 minus 2 into 0.4, that is around 0.3 volt, right? And the minimum voltage is 0.1. So the total range of voltages V naught can take is only 0.2 volt, right? And this is much smaller than this 0.9 volt that this voltage would have gone. Okay, and so for this reason, in most practical designs, we do not have this buffer. Okay, and we'll take this as the output voltage, right? And the moment we don't use the buffer here, the output impedance is no longer small, right? So this is no longer the ideal voltage controlled voltage source that we had here, right? And what we end up with is a voltage controlled current source that has a fixed transconductance GM and a high output impedance, right? The output impedance here is the R0 of this transistor parallel with this, right? So this is going to have a very high output impedance. So in practice, instead of having the OpAmp, we will have the OTA, or the operational transconductance amplifier, and it's denoted with this symbol. And this has some GM. Okay, so this will be the circuit we will have finally. This is during phase 1. And during phase 2, we connect it like this. Okay, so please notice that there is one important difference between using an OTA and an OpAmp, which is the following. So when you have the OpAmp, which is a voltage controlled voltage source, during the phase phi 2, you will have the equivalent circuit like this. You'll have the capacitor C here and the F here, right? And for this voltage controlled voltage source, this output voltage V0 is simply, if the gain is A, the output voltage will be minus A times Vx, right? And if the gain tends to infinity, for a finite output voltage V0, Vx has to go to 0. And this is what will give us our virtual ground condition, right? So for an ideal voltage controlled voltage source, the voltage gain is fixed, right? Which is simply A. And if we make A tend to infinity, the virtual ground voltage is 0 for all time instants, right? The moment you enforce the negative feedback, the virtual ground voltage will immediately, or sorry, the Vx voltage will immediately become 0, and we'll have the virtual ground condition. But the moment we have the OTA, during the phase phi 2, we'll have the equivalent circuit like this. Right? So even if you design this OTA alone to have a high or infinite gain, the moment you put it in feedback like this, the voltage gain from say Vx to V0 will depend on these capacitive loads, right? Because what OTA does is that it fixes the output current I0 to be minus Gm times Vx, right? So if I call the transconductance to be Gm, okay, and the output voltage will depend on these capacitive loads. So which means the voltage gain is not infinity at all frequencies, right? Because we don't have an output resistance, the voltage gain is infinity at DC. So the DC gain is infinity. But at high frequencies, we clearly see that the capacitor will provide a short circuit path and the output voltage will go to 0. So which means the gain will also drop to 0, right? Which means this voltage Vx will not be 0 for all time, right? Because the voltage gain is not infinity for all frequencies. And one thing we can say is the following: since the DC gain is infinity, the steady state voltage of Vx will be 0, So unlike an voltage controlled voltage source where this voltage Vx was 0 at all time instants, with an OTA, the voltage Vx only in steady state reaches 0 volt. Okay. So if you apply charge conservation to find the steady state voltage, we can still consider this virtual ground, that is this voltage Vx to be at virtual ground. So the steady state output will still be C by Cf times Vin, as we got with a voltage controlled voltage source as well, right? But what will be more interesting is to look at how this transient waveform looks like. So for that, let's do a quick analysis. Before jumping into a full-blown analysis using KCL, let's try to qualitatively understand what will happen. So during the phase phi1, we have the circuit like this. The capacitor is connected to Vin, and the OTA is reset along with the capacitor CF, right? So the voltage stored or sampled across the C in this polarity is some Vn, right? And the moment phi2 happens, what will happen? The equivalent circuit will be like this. Right? So if this is Vx, we just saw that Vx will not instantaneously become 0, right? So which means this capacitor voltage cannot change instantly, right? This is unlike the VCVS case where the VCVS enforced this voltage to 0. So the capacitor can transfer charge instantly, right? But now we know that this Vx will not be 0 instantaneously. So which means the capacitor voltage also cannot change instantaneously. So what will happen? Earlier, the capacitor had a voltage Vn charged in this direction. So just after phi2, the voltage across the capacitor will still be same, right? And since the left plate is 0, Vx will jump to minus Vn, okay? So that the capacitor voltage remains same. And this is just at the beginning of phi2. Okay. Following a similar argument, we see that this capacitor Cf was also initially charged to 0, right? So now since this plate is getting pulled to minus Vn, this will also jump to minus Vn, so that the voltage across Cf is still 0, right? And since Vx is jumping to minus Vn, what will be the current that is pushed out by the OTA? That will be simply plus Gm times Vn, right? So if I look at the waveforms, say this is the beginning of phi2. Okay, so till here we had phi1, and here let us say we have phi2. So during phi1, Vx was, that is this voltage, Vx was 0, right? Sorry, Vx is here, right? So Vx was 0. And the moment we have phi2, Vx jumps to minus Vn, right? Similarly, the output voltage V0, that was also 0 initially, and that also jumps to minus Vn. Right? On the other hand, the current I0, that will initially jump to Gm times Vn, right? So this is minus Vn, this is minus Vn. Okay, so the moment the current starts to flow out of Gm, this current will start to charge these capacitors. So which means the voltage across these two capacitors will increase, right? So Vx will start increasing. Similarly, V0 will also start to increase, right? And once Vx starts to increase, the current I0, which is simply minus Gm times Vx, that will start to reduce, right? So the rate at which the voltage increases will also reduce. So we'll have this kind of an exponential behavior where Vx finally settles to 0. Similarly, V0 will exponentially rise and settle to C by CF times V, right? And similarly here also, the current will become 0. Okay. So this is completely unlike we had with the VCVS, right? Where when we didn't have any on resistance, the voltage instantaneously jumped to C by CF times V, right? But now we see that even though we don't have on resistance or due to the switches, the voltage rises exponentially with some time constant. And what will be the time constant? Well, as we saw earlier, a time constant will depend on the rate at which this capacitor discharges. So let's see what is the equivalent impedance or the resistance looking into this side. Right, so let me redraw that part here. Right, so this is the circuit we have. So let's say this voltage is Vx, and let's say this current is Ix. Okay, and we are interested in finding the resistance looking in this direction, say Rx. So this current Ix will flow through the capacitor like this, right? And it will flow back into the GM like this. So if I call this current as Ix, what is Ix? Ix is simply GM times Vx, right? So which means the resistance will be Vx by Ix. That will be 1 by GM, right? So effectively the resistance looking into the right side of this capacitor looks like a resistor of 1 by GM, right? So we have the equivalent circuit like this. We have C and a resistor 1 by GM, which means the time constant will be C by GM. Okay, so this voltage Vx will follow this relation minus Vin into exponential of minus T by tau, right? And again, assuming that this is T equal to 0. Okay, and similarly, the current here will follow Gm times Vin, Gm times Vin e power minus T by tau, right? And similarly, the output voltage, how will it look like? So let me write it here. V0 will be the initial, the final voltage, that is C by CF into 1 minus T by tau, right? And the initial voltage, that is minus Vin, that will decay to 0 like this. Okay. So in short, when we have the equivalent circuit like this during the phase phi2, the time constant is C by GM, right? So when you have an on resistance also, say R-on, during the phase phi2, then the effective time constant will be 1 by GM plus R-on times C. Okay, so with R-on, the voltages will again rise exponentially like this, right? And the time constant will be 1 by GM plus R-on times C. And in practice, we usually make R-on to be much smaller than 1 by GM, simply because it's easier to design switches with low on resistance than making GM very large. Okay, so in practice, you will see that this time constant is dominated by 1 by GM. So this is roughly C by G. Okay, so this is what we expect from our qualitative understanding. And we can also confirm it by doing a full-blown analysis using KCL. And for that, we'll draw the equivalent circuit during phi2 again, right? And the initial condition across the capacitor C, we'll represent it as a voltage source as usual. And this value will be minus V in by S, right? And again, first we can ignore on resistance so that the analysis is simplified. So we have CF connected in feedback, right? So this is Vx and this is V0. So we can write KCL at this node and this node. So KCL at the virtual ground gives Vx of s plus V in by s times SC plus Vx of s minus V naught of s times SCF equal to 0. Similarly, KCL at this node, what does it give? The current leaving here, which is Gm times Vx of s plus V naught of s minus Vx of s times SCF equal to 0. So from these two equations, we can find what is V naught of s in terms of the input voltage, right? And we can take the inverse transform and find how the output voltage varies as a function of time. And that should give, that should be same as what we expect, right? So this should be the expression for the output voltage. Please take this as an exercise and find V naught of s, and then take the inverse transform and confirm that the output follows a profile as we expected. And from the transfer function, try to understand or try to guess why this jump is happening. Okay, so notice that this jump is happening in the opposite direction in which we actually want to go. Right here, the output has to go from 0 to a positive voltage of C by Cf times Vin. But instead, it initially jumps to the opposite side to minus Vin and then rises slowly, right? So from the transfer function, find why this jump actually makes sense. Okay, so let me draw the circuit we have once again. So this is 1, this is 1E, both are 2. So this is CF. These are reset to ground during the phase V1, right? And let me push this up. And in practice, we'll have this GM getting powered from a supply VDD, and it will be connected to ground as well, right? So this terminal, that is the positive terminal, in practice, we will not connect it to ground, right? Because please remember that this OTA will be realized by a differential pair like this, right? So if this is my positive and negative terminal, connecting this to ground will make the transistor go to cutoff region, right? So this will completely turn the transistor off and the op-amp will not be functional, right? So what we do is we connect it to VCM, right? That is the common mode voltage, usually around VDD by 2, okay? And even the input voltage here will be of the form VCM plus delta V in of t, right? So what will happen in this case? Well, at the end of the phase phi1, the voltage sampled across the capacitor in this polarity will be VCM plus some delta V in of some NPS, right? And what will happen when we put the circuit in phase 2? That is, we close the switches like this and put the capacitor in feedback. Well, from our qualitative understanding, notice that this voltage Vx jumps to minus V. Sorry, here, right? It jumps to minus V, right? And this is the voltage to which the capacitor was charged, right? So whatever voltage the capacitor was charged to, the negative of that voltage, right, is what the Vx will jump to. So which means here at the beginning of phi 2, Vx will simply jump to minus of VCM plus delta V in of NPS, right? So this is again a negative voltage and it will again turn the transistors off, right? So this is something we do not want. So what voltage we want this to jump to? Well, notice that the actual input is simply delta V in of t, right? So all we want is that the virtual ground voltage should jump by an amount proportional to this delta V. Right? So in principle, we want the virtual ground voltage to jump to minus delta V in of NTS, and it should be raised above a common mode voltage, right? So this will make sure that we have a differential current proportional to the differential input, which is VCM, that is this voltage, minus VCM minus delta V in of NTS, right? So we'll have a current proportional to this delta V in of NTS, that is GM times delta V in of NTS, right? That will be pushed out of the OpAmp, right? So this is the voltage we want Vx to jump to. So how do we do that? Well, for that, we need to make sure that we are sampling only delta V in of NTS and not VCM plus delta V. And how can we do that? Well, simply we'll connect this to VCM. Okay, so in that case, the capacitor here will get charged to the difference between these two voltages, which is simply delta V, right? So this will get rid of this. Okay, and now what will be the voltage to which Vx jumps to? That will be simply minus delta V in of NTS, right? But we want this to be VCM minus delta V in of NTS, that is this. So what we do, we raise this voltage to VCM. Okay, so this will make sure that the voltage to which Vx jumps to is minus delta Vin, that is the voltage that was sampled in the earlier phase, right? So negative of that voltage. So minus delta Vin, and since we are raising this by VCM, this will also raise up by VCM. Okay, so similarly, we also reset these voltages to VCM, right? Because the virtual ground here, we want it to be at VCM. So in phi 1 also, you keep this voltage at VCM. Okay, so how will the virtual ground voltage now look like during phi 1? This will be at VCM, right? And because that is the voltage to which we are resetting this. Okay, and during phi 2, it will jump down by an amount of delta V in, right? And then it will exponentially increase to VCM once again, right? So even the output voltage, how will it look? It will be same as this guy. Let me just rewrite it again. That will be C by Cf into 1 minus e power minus t by tau times. So this should have been V in here. I missed a V in here. So this should have been delta V in times this minus the initial voltage delta V into e power minus t by tau and plus VC. Okay. So let me copy paste this once again. So this is the final circuit we had, right? So how do we go about designing this? Well, from the given specification of the ENOP, we can find what is the signal to noise ratio we need for the ADC, right? And from this we can calculate what is the sampling capacitance we need, right? So from this, how can we find what is the GM we need for the OTA? Well, we saw that during the phase phi 2, the time constant is R1 plus 1 by GM times C, right? And this is roughly C by GM, right? So what we do is we make sure that this time constant is much smaller than Ts by 2. And from this, we can find what is GM. And once you know GM, we can find what is R1. And we make sure R1 is much smaller than 1 by GM. Okay. So this gives us what is the GM value you need for the OTA. But what about the minimum current you need from the OTA? Well, for that, let's see what happens in detail during the phase phi 2. So during phi 2, we have the equivalent circuit like this. So this is VCM. This is at VCM. This is Vx. This is C. This is Cf. Right? And at the beginning of phase phi 2, we saw that Vx will jump to VCM minus delta Vin, and the current I0, how will it look like? It will initially jump to Gm times the difference between these two voltages, that is simply delta V, right? So the current will jump to Gm times delta V. Okay, so which means depending on the sign of delta V, the maximum current that needs to be pushed or pulled out of this Gm must be this guy, right? So if the maximum voltage is some delta V max, so the maximum current that the Gm must be able to sink or source should be Gm times delta V in max. Okay, where Gm is the transconductance of this OTA. Okay, so one way to bias this OTA is to make sure that the bias current here is at least equal to this current, right? So if we take our differential pair, we can make sure that the bias current IB here is at least equal to this maximum current of Gm delta V in max. This will ensure that the OTA has enough bias current to source or sink this maximum current. But recollect that the waveform for I of t, I0 of t will look something like this. Say this is the phase phi 2. The current required, that is I0 of t, will jump to Gm delta V in at the beginning of the phase phi 2, and then it will decay to 0. Okay, so the current required from the OTA, that is I0, is Gm delta V in only in the beginning of the phase phi 2, right? So biasing the OTA for this current seems to be very inefficient, right? So let us see if we can bias this OTA at a bias current that is less than this value, right? And for that, let us understand in detail as to what happens when the OTA is operating during the phase phi 2. So let's consider the single stage OTA, right? So this is the differential pair. This is the bias current, say IB, and we have the PMOS current mirror load. Let me draw the diode connected PMOS in this side. Okay, so this is connected to the gate, right? So this will be the positive, and this will be the negative terminal. Okay, and this will be the output, right? So during the phase phi 2, how will the circuit look like? We have the sampling capacitor here connected to the negative terminal of OTA, right? Well, this is at VCM. Similarly, this voltage, sorry, from this node, we have the capacitor CF connected to the output voltage, right? And this is the voltage Vx. And the non-inverting terminal here is connected to VCM. First, let's assume that we have zero input, that is delta V in is 0, right? So Vx will remain at VCM, and this is also at VCM. So both these gate voltages are at VCM, which means the currents in these two transistors, they will split equally, and it will be IB by 2, right? So the same current here will flow here, and it will get mirrored in this PMOS branch. So we'll have the same current, IB by 2, right? So let me draw it somewhere here, IB by 2, right? So that will be the current flowing here. So which means the current that is flowing into the capacitor is 0. Okay. So now let us say my input is not 0. So what will happen then? At the beginning of phi 2, Vx will jump to Vcm minus delta V, right? So the differential current will be Gm times delta V in. Okay. So the currents in the individual transistors will be as follows. So here the gate voltage is lower. So that is for this transistor, the gate voltage is lower. So the current is minus Gm delta V in by 2. Here it will be plus Gm delta V in by 2. Again, the same current flows in this PMOS also, right? So that will get mirrored. So the current here will be plus Gm delta V in by 2 on top of the existing IB by 2. So the total current that is flowing into the capacitor, if I call it I0, what will that be? I0 is Gm times delta V. Okay, that will be the difference between these two currents. Okay. But now let us say we have the case where our bias current is such that Gm delta V in by 2 is greater than IB by 2. Right? So that is IB is less than Gm times delta V. Okay. So in that case, what will happen? Well, this current here, IB by 2 plus Gm delta V in by 2, right? So this will try to go beyond IB. But of course, that is not possible because the op-amp is biased only with the bias current of IB. Right? So the op-amp will say, hey, the maximum current I can provide is IB, so I'll give everything I have. So this current will be equal to IB, right? So this will become equal to IB. So this entire IB will get mirrored here, and I0 will also be IB, and this transistor will be completely cut off and no current will flow, right? So what will happen because of that? The capacitors here, CF and CE, they are getting charged by a constant current of IB. Okay. So which means the voltage Vx here, how will it look like? Ideally, we wanted it to do something like this. At the beginning of phi 2, it is jumping by delta V in, and ideally we wanted it to exponentially decay to Vcm again. But now we see that it is getting charged by a constant current of IB, right? So the voltage will increase linearly like this, okay? And the rate at which it increases will be IB by C, okay? So this is the voltage Vx, right? And this effect is called slewing, wherein the OTA is not able to provide enough current to charge the capacitor. So the entire bias current here is getting diverted and it is used to charge the capacitor like this. Okay. So when we have the OTA like this is at PCM. CF and C, right? And if I call this voltage Vx, till the point the current required from the OTA, that is Gm times Vcm minus Vx, till this becomes less than the bias current of the op-amp, we will have slewing, right? So wherein we have a constant current charging the capacitors like this. Okay. And the moment Vx falls to a value such that Gm times Vcm minus Vx is equal to IB, then the slewing will stop, right? So let us say this is the phase phi 1. Here we have phi 2 starting. So the voltage instantaneously jumps down by an amount of delta V in. And when slewing is there, we will have a linear rise in the voltage and the slope is IB by C, right? And till Vx falls below Vcm, this is Vcm, right? Till Vx falls below Vcm, by an amount of IB by GM, right? So remember, this simplifies to VCM minus Vx to be IB by G, right? So till this falls to this value of say IB by GM, we will have slowing, right? So till this time, slowing will happen. Okay. Let us now see what happens because of slowing. And for a simple case, let's say that we allow slowing to persist throughout phi 2. Right? So which means for the total available period of TS by 2, right, we are making the OTA loop. That is, the equivalent circuit is going to look something like this. So this is CF, this is C, this is my output voltage, this is Vx, and this is the bias current IB, right? So now, irrespective of the input voltage, the output is going to be same, right, at the end of the phase phi 2, because it's getting charged by a constant current, right? So this is definitely a ground case, and we do not want to have this. So what is the option? Well, we make sure that we limit slowing to a fraction of the available period, right? So let's say this is the total available period of TS by 2 for us. In this, let us say we allocate this much time for slowing. So this is my T slew. So the remaining period is Ts by 2 minus T slew. Okay. So how will the output voltage look like? Remember that this is the starting of the phase phi 2, right? So this is the starting of phase 2. This is phi 1. So during phi 1, the output would have been at VCM. And at the beginning of phi 2, it will jump to delta Vin, right? It will jump to VCM minus delta Vin. And since the OpAmp or the OTA is slowing, the voltage will rise linearly like this, right? And at this point, the current required from the OTA is less than the bias current, right? So the OTA will start to kick in and charge the output exponentially like this, right? And the settled value will be C by CF times Vin, or delta Vin of NTS. Right, so I'll just say delta Vin of delta Vin. Okay. So this is the voltage IB by GM. Right. So now, how will the settled waveform or the settled value look like? Well, we saw that the output has a profile given by this. So this is the output voltage when there is no slowing. That is, we have this exponential settling happening throughout Ts by 2. Right? In this case, the initial voltage was minus delta V, right? And the final voltage is this guy. But now, when the exponential settling happens, what is the initial voltage? That is this IB by GM, right? VCM minus IB by GM, right? So we already have VCM. So the initial voltage is IB by GM, right? And the final voltage is still this fellow. So we'll have the same thing here. So what is the voltage at the end of phi 2, that is at this time instant? If I call this to be some t equal to 0, this will be t equal to Ts by 2 minus T slew, right? So the output voltage V0 will be the output voltage. This is at the end of phi 2 will be delta V in C by CF 1 minus e power minus Ts by 2 minus T slew by tau. Similarly, we have minus IB by GM e power minus Ts by 2 minus T slew by 2 tau plus VCM. Okay, and please notice that this time t slew is a function of the input voltage. In this case, when we had an input of delta Vin, the voltage Vx here jumped by delta Vin and it had to rise linearly, and only when it reached this difference of IB by GM, slowing stops. But if the voltage was smaller, it might have jumped to this point, right? And it will again rise linearly with the same slope. So which means slowing will stop at this point itself, right? So this time for which slowing happens, t slew, is obviously a function of the input itself, right? And since t slew is a function of the input, here we see that we have t slew appearing with an exponential relation. So we'll have an error voltage that is proportional to e power t slew by tau, right? And since t slew is a function of the input, this will in turn result in nonlinearity. Okay. And the solution to this problem is to make sure that slowing doesn't happen for a longer period, right? And the moment you do that, the exponential factor, that is this guy, will be e power minus ts by 2 minus t slew by tau. Okay. So if you make sure t slew is not a large number, then this factor will be small. And this will in turn help in reducing the nonlinearity, right? So usually many times when you start to design, people do the following. They choose the slowing time t slew for a maximum input of delta V in max to be around ts by 4. That is, you allot half the time for slowing and remaining half you allow for the linear exponential settling. Okay. And with this choice, if you find that the linearity you get is not good enough, you can improve the linearity by reducing this slowing time. And this can be done by increasing the bias current of the OTA. Okay. So let's stop at this point and continue from the next class.